Good morning, all of you. Yesterday, we have seen some concentration terms in that molality is left. Molality is another concentration term in which we have to find the number of moles of solute in 1000 gram of the solvent. Means mass of the solvent should be in kg and number of moles of solute upon mass of solvent in kg. That means in 1 kg of solvent, what is the number of moles of solute? That will give you molality. Molarity is an important concentration term. Mole fraction, an important concentration term. Molality, an important concentration term. So these three terms we require very much in this forthcoming topics. Molality is the number of moles of solute upon mass of solvent in kg. Means we are calculating the number of moles of solute. What is the number of moles of solute in 1 kg of the solvent? So these are the concentration terms. Mass percentage will be coming as a side part of a numerical. Next, we are going to the solubility of a solid, then solubility of a gas. We know that many solids are soluble in water. Sodium chloride and calcium chloride are soluble in water, polar solvents like water. But benzene and naphthalene are not soluble in water. Benzene and naphthalene are soluble in organic solvents, for example, CCl4. So, polar solutes are soluble in polar solvents. Non-polar solutes are soluble in non-polar solvents. Means like dissolves like. When we call a solute is soluble in a solvent, when do we call? You are taking some solute and mixing with that solvent, and you see that if it is soluble, then you will not see any solute in that. Means you will be getting a homogeneous solution. So again you add a little bit solute, it is soluble. You stir it, it is soluble. Again you add, it is soluble. You stir it, you find it is soluble. You keep on adding till it does not soluble in that. It does not getting dissolved in that solvent. So first we added little bit, again you added, again you added. In all these cases, you found that it is soluble. Now we say it is the process of dissolution. You kept on adding the solute, till it is not soluble. Means now the dissolution stopped. At any moment now, the dissolved substance can come out as the solid. That coming out as a solid from the dissolved state is called crystallization. So dissolution and crystallization are two opposite processes. Dissolution means getting soluble or getting dissolved. Crystallization means coming out of the solution. So dissolution and crystallization are two opposite processes. Now, when the solution gets saturated, in that position, some of the solid particles can get into the soluble state, and some of the soluble state particles can come out to the solid format. So there is a to and fro processes, or we can say it is in a dynamic equilibrium. Some solutes are getting changed into the soluble format, and at the same time some soluble part is changing into the solid format. We say a dynamic equilibrium is reached. Now, in this case, we were dissolving the solids in the liquid. Solids in liquids, that dissolution process can be enhanced by increasing the temperature. When the temperature is increased, you can dissolve more and more solid. You can dissolve more and more solute into the solvent. So the solution becomes saturated solution, super saturated solution. So, temperature has an effect on the solubility of a solid, but pressure has no effect on the solubility of a solid in a liquid. Pressure has no effect. The pressure terms come when it is a gas, when the gas is as a solute, when the solute is a gas. The pressure term we use only for gases. Gas means pressure, pressure means gas. Suppose the solute is a gas instead of a solid. Suppose the solute is a gas instead of that previously what we said, that's solid. Now, as you increase the pressure of the gas, more and more gas will be soluble in the solvent to get the solution. You know that soda water, in which carbon dioxide is present, soda water is made by passing carbon dioxide through water at high pressure. When you increase the pressure of the carbon dioxide, more and more gas will be getting dissolved in that water, and we call it as soda water. When you release the pressure, the dissolved gas will be coming out, giving the drink a sparkle. Carbon dioxide rushes out when you release the pressure, when you decrease the pressure. The carbon dioxide gas rushes out the solution, giving a sparkle, that is to give an appearance to that drink. For that only they release that carbon dioxide gas. Otherwise, there is no other purpose of that. So carbon dioxide gas is dissolved in water to make soda water. If the pressure of that carbon dioxide gas is more, then more and more gas will be dissolved in that water. So soda water is prepared under high pressure. High pressure. The amount of carbon dioxide dissolved in that solvent, in that water, is proportional to the pressure of the gas, the pressure of that carbon dioxide gas, the pressure of that individual gas. We call that pressure, individual pressure, we call it as partial pressure. Now here air is there. We cannot say partial pressure for this air. It's the total pressure exerted by many gases. Carbon dioxide, oxygen, nitrogen, water vapor. So many gases are there in this air. Each gas is exerting its own pressure. We call it as partial pressure. What is the total pressure? We know that it is 1 atm. 1 atm pressure. So this individual pressure is called partial pressure. The amount of carbon dioxide dissolved, that amount of carbon dioxide dissolved, we talk in terms of the concentration. Which concentration term is appropriate here is XB, that is mole fraction of carbon dioxide. XB. XB is proportional to the pressure of that carbon dioxide, that is PB, pressure PB. B is the solute, carbon dioxide is a solute here. So XB is proportional to PB. The amount of carbon dioxide dissolved in this particular solvent, that amount of carbon dioxide is expressed in terms of XB, mole fraction of carbon dioxide. This XB is directly proportional to PB, or we can say According to more and more PB, XB will be increased. Henry's law gives a relation between PB and XB. Henry's law states that the partial pressure of a gas in vapor phase is directly proportional to the mole fraction of the gas in the solution. Partial pressure of a gas, that is PB. Partial pressure of a gas, for example, carbon dioxide. Carbon dioxide pressure is PB. That PB is proportional to XB. Partial pressure of a gas in vapor phase is directly proportional to the mole fraction of the gas in the solution. That is, PB is proportional to XB. This is the common form. Henry's law in its common form or general form, PB is proportional to XB. So PB is equal to, that proportionality sign can be replaced by putting a constant called Henry's constant, that is KH. PB is equal to KH into XB. Let's see those things. Henry's law. PB is proportional to XB. PB is the individual pressure. We call it as partial pressure. Partial pressure, here it is of carbon dioxide. Individual pressure is called carbon dioxide. Now, PB is equal to KH into XB. KH is called Henry's constant. Now, PB is the pressure. Unit of pressure will be there. XB is the mole fraction. No unit. So, KH will have the units of this pressure. Why? Because XB has no unit. What is KH? KH is equal to PB upon XB. So this is a general format or common form of Henry's law. The partial pressure of a gas in vapor phase is proportional to the mole fraction of the gas in the solution. Now PB is proportional to XB, that is Henry's law format. We can say XB is proportional to PB. XB is proportional to PB. So here again XB is equal to KH into PB. But this is not the general form or common form of Henry's law. But this is also correct. So here the KH, what is the unit of KH? That is the inverse of pressure unit. So KH can have two types of units, pressure unit or inverse of that. So first you have to check what is the unit of KH. Accordingly you have to apply whether equation 1 or equation 2 which is to be used. KH can have both units. Depending upon the KH unit you have to select which is the equation to be applied. General equation 99.9% you will see PB is equal to KH into XB. Now let's see what are the pressure units. I told you KH has the unit of pressure. KH has the unit of pressure since XB has no unit. Every gas has got a typical KH value. As KH value increases, solubility decreases. This is the relation. What is the significance of KH? You can check the KH value. You can check the KH values of different gases. As KH value increases, solubility decreases. Now we are dissolving a gas into a solvent to make a solution. Gas means pressure. Pressure has got an important role on the solubility of a gas, and that relation is expressed in the form of Henry's law. What is Henry's law? Henry's law states that partial pressure of a gas in vapor phase Pb is proportional to the mole fraction of the gas in the solution. Now let's see. We have learned that Pb is equal to Kh into Xb. Kh into Xb. So Kh will have the unit of Pb. Now I'm concentrating on this pressure, units of pressure. Conversion factors are 1 atm. Pressure can be in atm. You can express the pressure of a gas in atm. 1 atm, you can express this in terms of bar also, 1.013 bar, which is equal to 76 centimeters of mercury, which is equal to 760 millimeters of mercury, which is equal to 760 torricelli, which is equal to 1.013 into 10 to the power of 5 Pascal. So, pressure has got so many units. ATM, this is the biggest unit. This is the smallest unit. 1 atm is equal to 1.013 bar, which is equal to 76 centimeters of mercury, which is equal to 760 millimeters of mercury, which is equal to 760 torricelli, which is equal to 1.013 into 10 to the power of 5 Pascal. Now, this pressure is individual pressure. We call it as partial pressure. When you consider air, it contains so many gases: oxygen, nitrogen, carbon dioxide, water vapor, rare gases. So, here this total pressure, sea level, we take it as 1 atm. 1 atm, sea level 1 atm. On the top of a mountain, these gases are less, so the pressure is also less. So individual pressure, if I consider the sea level, 1 atm is the total pressure. If you see the mole fraction of this, mole fraction of this, mole fraction of this, all the mole fractions, when you add, you will get this 1 atm. When you add all these mole fractions, you will be getting this 1 atm. So what is the individual pressure? What is the individual pressure of this carbon dioxide? What is the individual pressure of this carbon dioxide? Or what is the individual pressure of nitrogen? What is the individual pressure of this oxygen? Accordingly, this will be soluble in water. Water means in water bodies. For example, river water, lake water. According to the individual pressure, how much oxygen is soluble in lake water or water in the river or in a pond, that depends upon the individual pressure of this oxygen. How much nitrogen is soluble, that depends upon the individual pressure exerted on that water body. So, according to the individual pressure, the gas will be soluble. Total pressure, this 1 atm, is the sum of the partial pressures. Total pressure, this 1 atm is equal to sea level, I am talking about. Total pressure of 1 atm is equal to the sum of the partial pressures. Partial pressure. You can find out the mole fraction also. You know that last year you learned the mole fraction of nitrogen in air. Mole fraction of nitrogen in air is 0.78. Mole fraction of nitrogen in air is 0.78. So, this mole fraction, what is this mole fraction? Xb. Oxygen also has got 0.19 and the rest is the other gases, mainly nitrogen. Main quantity of this air is nitrogen. So mole fraction of different gases you can find out from air. Using these mole fractions, you can find out different data. 99% questions will be asked on the basis of Henry's law in the general form. So here you can substitute XB if the partial pressure is given. This 0.78 I am talking in the case of air. But at different times, this partial pressure of this nitrogen can vary. See, carbon dioxide is dissolved in water at a higher pressure. Higher pressure. So these pressures, individual pressures are different, mole fractions are different. For gases, that KH value is different. In air, there are many gases. We know the pressure of each gas is called partial pressure. Now, partial pressure, how can you find out this partial pressure? Mole fraction you can find out. How can you find out the partial pressure of a gas? In the case of air, total pressure is 1 atm. Partial pressure of a gas. Last year we learned partial pressure of a gas is equal to total pressure into its mole fraction. Now this XB, we learned this XB. Till now we learn mole fraction in the form of XB. In the case of a gas, XB we take in solution. In the case of a gas, we replace it by YB. Partial pressure of a gas is equal to total pressure and its mole fraction. YB. So if you consider air, then for example, partial pressure of nitrogen means individual pressure of nitrogen is equal to, what is the total pressure air at sea level? That is 1 atm into, in air, sea level, the mole fraction is 0.78. So, mole fraction has no unit. So, what is the partial pressure sea level of nitrogen? That is 0.78 atm. 0.78 atm, that is the partial pressure of nitrogen. What is the mole fraction of nitrogen? That is 0.78. 0.78 is the mole fraction, that is this YB. So you see, in the means air at sea level, this 0.78 same, but the units are different. Sea level air, 1 atm is the total pressure. Its mole fraction is 0.78, so 0.78 atm is the partial pressure of nitrogen. Now nitrogen in a cylinder will have different different partial pressure. Suppose we have a mixture of gases, nitrogen and oxygen in a cylinder. Total pressure will not be 1 atm. This is in open, sea level. In that cylinder, total pressure will be different. Total pressure will be different. Its mole fraction will be different. So its partial pressure will be different. This is what I have written is in the open air, sea level, not on the hill station. Again, we are going back to, what we are learning, partial pressure means individual pressure. This YB, this is the mole fraction. This equation we have learned in class 11th. In Henry's law, what is Henry's law? PB is equal to PB is equal to KH into XB. XB is the mole fraction in the solution. XB is the mole fraction in the solution. YB is the mole fraction in vapor phase. XB denotes the mole fraction in the solution. In the solution. YB is the mole fraction in the vapor phase. In vapor phase. Alright. So once again we are coming back to PB is equal to KH into XB. You will have numericals based on this equation. Now coming to KH. I told you as KH increases, solubility decreases. Now I'm taking two gases. Gas. Helium and hydrogen. KH value I am giving at a particular temperature. KH value that is helium 144.9, hydrogen 69. At a particular temperature I am giving 293. 293 Kelvin, temperature in Kelvin. So which is more soluble? Looking at the KH value, you can say that which is more soluble. As KH increases, solubility decreases. Solubility means mole fraction, XP. Solubility decreases. So, see, KH is increased compared to hydrogen. KH has got very high value. So, solubility. So, helium is less soluble. Looking at this value, we can say helium is less soluble. Helium is less soluble. Since it is less soluble, this helium is utilized in the cylinders of scuba divers who dives deep down the sea. Their scuba divers tanks used by scuba divers are filled with air diluted with helium. They need air, but that is diluted with helium. Because helium will not get dissolved in our blood. If it is not helium, what will happen? The nitrogen of the air nitrogen solubility is very high. Nitrogen solubility in our blood is very high. So this nitrogen gas will get dissolved as we go down, the pressure increases. So due to the increase in pressure, nitrogen will get dissolved in our blood. And when the scuba diver comes up, the dissolved nitrogen will be coming out from the blood in the form of bubbles, and these bubbles will be remaining at the joints of bones, and that will give immense pain, that will give a severe pain. That pain is very high. So to avoid that pain, that pain is called bends. To avoid that pain, to avoid bends, that is blocking of capillaries, blocking capillaries by these bubbles, as well as the toxic effect of high concentration of nitrogen in blood. The tanks used by scuba divers are filled with helium, that filled with air diluted with helium, filled with air that is diluted with helium. Otherwise, what will happen? Nitrogen, which has got high solubility in blood, will be soluble when the diver goes down. When the diver comes up, the dissolved nitrogen will be coming out in the form of bubbles, and it will block the capillaries, and the pain will be a severe pain. So that is the significance of the sketch. As sketch increases, solubility decreases. So looking at the KH value, you can select which gas is to be selected for what purpose. Here, compared to hydrogen, helium has got less solubility. Now, what about the temperature difference? If the temperature is high or low, what about the solubility of a particular gas? So in that case, I'll be taking the same gas at different temperatures. When I took this helium and hydrogen, I took same temperature, different gases. Now I'm going to take same gas but at different temperature. Same gas means, for example, gas is oxygen, O2, O2. Temperature is different. Temperature, that is low temperature to 93 Kelvin and high temperature, for example, 303 Kelvin. Now, at this cases, KH value changes. KH value 34, KH value 36. When the temperature changes, KH value will also be changing. As KH value changes, solubility changes. As KH value changes, solubility changes. So you see, when the temperature is high, KH value is also high. When the temperature is high, KH value is high. When the temperature is high, at higher temperature, the dissolved oxygen will go up. So the amount of oxygen in the water will be less. Then fishes become uncomfortable in hot water. Why? Because dissolved oxygen is very less. They cannot get enough oxygen to breathe. So when the temperature changes, KH value, when the temperature is increased, KH value increases. So you know that temperature and solubility, as temperature increases, solubility decreases. Solubility and KH value are inversely proportional. Here solubility is decreased, that means KH value is high. So in this way you can relate these three things. This you know already, as temperature increases, solubility decreases. As temperature increases, solubility decreases. And solubility and KH value, what is the relation? That is inverse relation. As KH value increases, solubility decreases. So this is the relation between temperature and solubility, KH and solubility. So which gas is more soluble? If the gases are different, which gas is more soluble? You can check the KH value and say which gas is more soluble. What are the applications of Henry's law? The scuba divers I talked about. Then to increase the solubility of carbon dioxide in soft drinks and soda water, the bottle is sealed under high pressure. Another application of Henry's law is at higher altitudes. I was telling sea level, sea level, sea level. But at higher altitudes, you know that the amount of different gases present in that air on a hill station is very less. So presence of oxygen is also very less. Partial pressure of oxygen is very less, we can say. This leads to low concentration of oxygen in blood and tissues. So people living at high altitudes and climbers, means mountain climbers, become very weak and are unable to think clearly. This disease is called anoxia. Anoxia. So people who are living at high altitudes or hill stations, what happens there? The partial pressure of oxygen is very less. If partial pressure of oxygen is very less, means the amount of oxygen that is present in the blood is very less. So their brain will be getting very less oxygen. So they cannot think clearly. This disease is called anoxia. So people who are living at sea level are more intelligent than who are living at hill stations. Okay, thank you. I'm stopping now.